Hello, in this short video I want to show you how to draw a total state diagram for a transition table. Now the transition table has stable and unstable states, and we need to account for every square in the table. So it's called a total state diagram because it includes both the input and the output. Now it's normal to put the output on the right of the input when writing the total state, but in this particular case, for this type of diagram, we are going to put the output in front of the input because it's easier to read like a conventional Carnot map. So there's no reason why we can't do that. So we call it total state, and to remind ourselves, we just write y1, y2, x1, x2. Now the first thing we have to do, we have to put the stable states on the diagram, and then the stable states will be connected by the unstable states to each other. So we're going to do that now. We have 6 stable states. So on the top here we're going to put 0, 0, 0, 1. And we're just going to put a little asterisk in it to let us know that it's the stable state. And then underneath that we are going to put the stable state pair 1010 and 1011. 1010 and 1011. Now the stable state pair is always connected because we can move from 1011 and 1010 quite freely between the two of those stable states. Then we have another stable state pair 1111 and 1110. So we can move freely between those. And then finally our last remaining stable state is 0100. 0100, following this writing of the total state. So we put that down here. 0100. Okay, so now, having done that, we can begin to connect our states as required. Now the first thing we know or notice is that we have a cycle coming out. Now I've tried to fit it in here, but it's going to get a bit crowded because of the edge of this, unfortunately. But we should be able to manage fairly good. I wish I had more room out there, but let us expand it this way. Let us come around like there and put a state here. Where do we go when we leave 0001? Well, there's only 2 directions we can go, left or right. So we're going to 0000. and that puts us to row 2, which is 0 1 0 0. Sorry, it's 1 0 0 0. And that goes to one one 0 0, and then finally to 0 1 0 0. Okay, so you see that we have a cycle here in this column. When we leave 0 0 0 1, we move to the left to 0 0 0 0, which sends us to row 2, and it has to be in the same column, so we have 1 0 0 0, which sends us to row 3, so we have square 1 1 0 0, which sends us to row 1, so we have 0 1 0 0, which is stable. So that will happen every time, that cycle will happen every time we transition between this stable state and this one. So what can we do next? Well, we can proceed by realizing there that this other one can in fact move to the right as well, so we can go to 0 0 1 1. And that brings us straight to that. So if we move to the right, we got to go to row 3, and it's in row 3 we're in the same column, so it's 1 1 1 1. So that square transitions to that. Now we have a stable state pair here, so we can only have one way to get out and one way to get out of each of those, because the other way is inside of the pair. So in the case of the 1 1 1 1, we can go to the left to come to 1 1 0 1. Which is going to send us back to 0 0 1. So we've got 1 1 0 1. And that sends us back. As I said, it would be better if you used a whole page to do it, but I'm trying to do it small here because I have a limited window and I don't want to have to be shifting the paper around for you. Okay, so that's the method of operation that we're trying to follow. Now, what happens next is that we have this 1 1 1 1 0 going to 1 1 0 0, but we've got that here already. Go that away. So that takes care of that stable state pair. And we've taken care of, let us put little asterisks there to let us know that those are stable states. So we need now to take care of this and this. Okay? So we haven't taken anything out of this one yet. So we can deal with whichever one we want to deal with. But this one's going to go in two directions because it's single. And these double ones are going to go in two directions. Okay, so if we have the 1011, we can move to the left to go to 1001, which will send us back to our original one at the top. So basically we slip one in here. And I'm gonna have to write fairly small in him. But that is 1001. 1001. Now what about here? We have 1010. 1010 can move only one way to 1000. But we have him already here. So as you can see, we've completed that, we've completed this, we've completed that. So the last one we need to complete now is this one. And we are going here in two different directions. One carries us to 0101, which will send us back to 0001. So we have another one here that we can put in. Zero.
School if you want to.
Try a cheese sandwich.
Try start it with a cheese sandwich. She brings it back home and give it the birds. You can only try her.
So as we can see here, this goes from 0100 to 0101. 0101. And that carries it back to 0001. The last one we need to complete our diagram is from 0100 to 0110. 0110, which goes to 1010. So there is your total state diagram with the transition table. And the last thing we need to do now is to look for races in the transition table. And what do we find? Are we going to have any races? Well, we have to look row by row. We're going to see here that when we move to the right, we're going to get a race because two variables are trying to change at the same time. So that is one race in row 1. Then we're going to have a race here in row 2 as well when we try to move from this one to this one, because once again both of them have to change. In row 3 we are going to have a race here when we try to move from this stable state to this one, because both of them have to change. And in row 4 we're not going to have any races at all. So we've got 3 races to consider, and what we're going to do is we're going to draw the races as separate diagrams so as not to complicate, confuse, and make a mockery of our total state diagram. So we can come down here so, and we can say race 1. Now remember that the race doesn't start until we move away from the stable state. So we can start the race with 0, 0, 1, 1 as an unstable state if you want, because 0, 0, 1, 1 is the one that we come to. See here? We don't have any race starting here. It is when we begin to move, when we move from 0, 0, 0, 1 to 0, 0, 1, 1 that the race actually starts. Okay, so let us consider what happens with the race. Well, we can go to any of the other 3 rows once the race starts. So in our original diagram we followed it to the 3, which was quite okay. So we'll put that back here. So now we have to just look at the other 2 places we can end up in the transition table, which would be here, which would ultimately send us to here, or here directly. So basically we are going to have a critical race, because we can either land on 1, 1, 1, 1, or we can land on 1, 0, 1, 1, either directly or via this one. Okay, so it looks like, it actually looks like this then. And this is the other one that we have, which is 0, 1, 1, 1. Okay, so in a normal situation we would only be able to move from a square in 2 directions. We can exit the square either to the left or the right. But when we have a race going on, we can do 3, because we are trying to change from 0, 0 to 1, 1, and that would happen perfectly if we did this, or if we had one changing before the other, it could go there or it could go there. Okay, so 0, 0, 1, 1, as you can see here, is an intermediate square. Sorry, 0, 1, 1, 1 is an intermediate square, which is an unstable one, but it will send us to this one, which is a stable one. So that is the reason why We can either take there or there, but we always end up here if we go that path, if we go 0, 1 or 1, 0. And if we go can manage the 0, 0 to 1, 1, we will end up there. So we can write here critical race, because we can end up at one of two different destinations, because these are both stable, right? Those are both stable. Alright, so hopefully now you understand the race idea. But let us look at race 2 and then finally at race 3. Race 2. What is our launching point for race 2? Well, it would be when we switch from this stable state to this unstable state here. So the unstable state that launches race 2 is 0, 1, 1, 0, the square 0, 1, 1, 0. Okay? And in a perfect world, it would go to 1, 0, 1, 0. But since we can't get that to happen, we would get two more exit points. And we have to write something, but let us look at those two more exit points more carefully up here at the transition table. We are on square this one. And in a perfect world, we're going to go to this one. But we can either end up with this one or this one. If we end up on this one, we are on square 1, 1, 1, 0. But if we go here, we have an unstable state at 0, 0, 1, 0. Which sends us, where does it send us? It sends us to row 2, which is 1, 0, 1, 0. So basically, once again, we have a critical race. Finally, let us look at race 3. Now, race 3 is in the third row and happens when we move from 1, 1, 1, 1 to 1, 1, 0, 1. In a perfect world, we would go to 0, 0, 0, 1. But because it's not a perfect world, we could either go to 0, 1, 0, 1 or 1, 0, 0, 1. Let us look at those two. Okay? We could either end up at 0, 1, 0, 1, and if we do, it's unstable, but it will carry us to 0, 0, 0, 1. See? Or if we end up at 1, 0, 0, 1, it will also carry us to 0, 0, 0, 1. So look at it. Whichever way we go, we are going to end up at 0, 0, 0, 1, which is stable. So this is a non-critical race because it only has one outcome. No matter how fast we go or what path we take, the outcome is certain. So that's it, folks. I hope you all do well in your test. And thank you for watching the Stephen Mendes channel. And we'll see you soon again.